Hello folks. In this video we're going to be talking about optimizing shapes. That means either finding a minimum perimeter, so the smallest perimeter that could go around the shape, or its maximum area. And we're going to do that in the form of an activity here. So this activity starts by saying local parks officials have been given a grant to beautify its facilities. Along with new playground equipment and repainting all of the buildings, a garden is to be planted somewhere on the grounds. 3 different locations have been chosen for the garden. However, the brick used to line the perimeter of the garden is quite expensive. You will examine the 3 different locations for a garden area of 20 square meters and decide which option will be the cheapest to border with the chosen brick. So we're specifically doing 20 square meters, and that has to be the area of the garden. We're going to use Geometry Sketchpad to investigate 3 different scenarios in this. And the first one we're going to do is a circular garden with a fountain. So if we go and take a look at the Geometry Sketchpad here, here are the 3 different shapes we're going to use, but we're starting with the circular garden. Now, I want to have an area of 20 square meters. You can see here. Now, first of all, there is an error in the Sketchpad file, and I didn't change it. It says square centimeters here. We're doing square meters. It doesn't matter what the unit is. As long as we get the number correct, we're good, okay? So, and it's the same problem with all 3 of them, so I'm not going to repeat that discussion for those 2 shapes. So we're trying to get this area to be 20. Now, with a circle, you don't really have much choice. All you can do is make the circle bigger or smaller by changing its radius. So if I want an area of 20, and it's quite difficult to get it perfectly on 20 here, I'll do my best. That's pretty close, okay? That's about as close as I can get it. There's no other option, and you might not understand what I mean by no other option, but you'll see in a minute what I mean by that with the other shapes. Here, there's only one choice. Our radius has to be 2.54, and our circumference has to be 15.97. There's no choice there, okay? So as soon as you get your your area at 20 square meters, you now have your circumference value. So there's only going to be one possible set of dimensions, which is going to be that set of numbers, the radius and the circumference. And I'm just going to go back and take a look at them again. So the radius is 2.54, and the circumference is 15.97. And that's it. That's the only option we have. Well, it says the committee's second option is near the entrance of the park, and here the garden would surround the welcome sign to the park. For this case, you must consider at least 5 different dimensions for the length and width of the garden. So here we're going to be using a rectangle to go around the sign. So what is going to be the rectangle that gives us the minimum perimeter when our area is 20? Now, let's go take a look at the Geometry Sketchpad for that. So again, we want our area to be 20. Well, what are the different types of rectangles that we could get that would have an area of 20? So if I go like, let's see here. Again, very difficult to get it perfectly, but that would be an area of 20. And we could write down the information for our length and width of that. Let's see if we could do something else. So if I went like this and got an area of 20, okay, which is somewhere around there. So we want to do that over and over again until we get the smallest possible perimeter. So you'll see here that the perimeter is 18.87. If I go back to a similar shape to what I had before, I think That's about as close as I'm going to get. The perimeter is 18.38. And you do that over and over again. Now, I'm going to try one more here. Remember, we're trying to get the smallest perimeter we can possibly can, right? So this one's 17.95, which is the smaller perimeter than before, but we have an area similar to the one. Now, what shape does this seem to be starting to look like here? Okay, so I actually did this experiment earlier and took a bunch of data down. And you can see that my areas are all pretty close to 20. I wasn't able to get it perfectly. But if you look at the length and the width, here the length and the width is like almost 7 and around 3, and then almost, like around 8.5 and around 2.3. As soon as my length and width started to get closer and closer to the same value is when my perimeter got to its smallest amount. And that's actually the solution to this problem. What shape of a rectangle gives us the minimum perimeter? Well, it looks like if the rectangle is a square, we would actually have the minimum perimeter. So what's special about a square? Well, first of all, some of you might be saying, but sir, a square is not a rectangle. Yes, it is, because the definition of a rectangle is a shape that has opposite sides that are the same length and all the corners are 90 degrees. It doesn't have to be that the two sides that are adjacent to each other are different lengths. It could be that they are the same length, and that is still a rectangle. So in this case, because we are trying to get a let me just get my pencil ready here. Because we are trying to get an area of 20, we could actually now, because we know that our shape is a square, we know that the area of a square is length times width, but the two things are the same, so we usually say that that's side squared. That means that I can replace the a here by 20, and I can actually calculate what would be the best side length for this square, and that is by square rooting. So I'd have to square root 20 to get my side length. If I do that on my calculator here, I get 4.47. So if my side length is 4.47, I would get my minimum perimeter, and I can actually calculate that minimum perimeter. We know that the perimeter of a square, let me just draw a quick square here. So if we now know that one side is 4.47, and we know that all side lengths are the same, if I call this S, we know that the perimeter of a square is 4S. So if I do 4 times 4.47, the number that I just calculated from the area, I can actually calculate what that perimeter is going to be. So 4 times 4.47 is equal to 17.88 meters. So the important thing here is, if you're reading a question that says, find the minimum perimeter of a rectangle, the key word is minimum. You can't use length times width as the area of that shape, because the minimum perimeter of a rectangle requires that the shape be a square. What is also interesting about this relationship is that if we talk about what is the maximum area of a shape, the maximum area of a shape for this case here, which is a rectangle, will also be a square. That means that if you have the maximum area, you also have the minimum perimeter. They work hand in hand with each other. If you get a minimum perimeter, you have a maximum area. If you have a maximum area, you get a minimum perimeter. So this is the way you would solve either one of those types of problems. If they're asking you to maximize the area of a rectangle, use a square and use these two formulas. The area is equal to side squared formula, and the perimeter is equal to 4S formula. So these two formulas here are very important to calculating what we call the optimum shape. Okay, so optimizing in this case is going to mean both finding the maximum area and the minimum perimeter. So the next shape we want to look at is a triangle, and it has to be a right-angled triangle. So the committee's final option is to use the corner of the park. And again, we're going to use Geometer Sketchpad to investigate this. Now, I've already done this, but I'm going to show you on Geometer Sketchpad what this looks like. So we now have our triangle down here. Our area has to be 20. It is a right angle triangle. So what are the different shapes that we could have? Well, I could go way out to here, and that would be 20 approximately. Okay, close enough. I could change this height and then bring this in. And that would be approximately 20 as well. Now, knowing that the optimal measure for a rectangle was a square, can you hypothesize what would be the optimal shape for a right angle triangle? What would be special about that right angle triangle? What's going to give us our minimum perimeter? Okay, I'll just show you another one. Can you see something happening with this length here and this length here? If we go back to the table here, now I didn't do 8, I only did 6, but you can see my perimeters were pretty similar for the first two and a little bit different for the last 3. The smallest one I could get was 21.61 with an area of about 20.04. Now look at the measurement of the height and the base. They are pretty close to being the same. What is the name of a triangle that is right angled that has two side lengths that are almost the same? And that is going to be a isosceles triangle that is also right angled. So that is going to give us our minimum perimeter and our area of 20. Now, is that also going to give us our maximum area? So let's take a look here at another Geometer Sketchpad file. So let's say in this case, we want our perimeter to be set at 15 centimeters or 15 meters, whatever we want the unit to be. What is the triangle that's going to give us the maximum area? So we want our perimeter to be 15. So let's drag this in first and get a perimeter of approximately 15. So our area here is 9.17. Okay, 9.17. So let's change our shape. Let's go back to an area of 15, a perimeter of 15. Oh, I might not be able to get it with this one. Too long, so let's bring this down a little bit here. So there's our perimeter of 15, but our area is 3.8, which is much smaller than the 9 that we had earlier, right? If we hypothesize that we need, again, probably our isosceles triangle, just going to try to make it as close as I can here. So now I have 9.6, 9.58 approximately, and that is a lot bigger than the 9.1 we had earlier, and definitely a lot bigger than the 3 we had just previous to this. It looks again like we have an isosceles triangle, and that is the case. So what we're going to do now then is we've optimized our right angle triangle. We know it has to be an isosceles triangle. How does that change the equation? So in the square example, where we had a rectangle, we changed the equation of the rectangle to match the equations of squares, so side squared and 4L. How does doing that kind of thing for a right angle triangle affect it when we have to have an isosceles triangle? So we're going to use some algebra to find some special versions of those equations, the perimeter and the area of a isosceles triangle. So this is going to be how we find the maximum area that has a set perimeter or a minimum perimeter that has a set area. Both of those cases are going to be covered by these formulas. So the first thing I want you to notice is I've got a right angle triangle over here, and I've set both side lengths to be the same, and I called those side lengths A. Now I don't want to use numbers here, I want to use algebra, because if I can prove the two equations, or not prove, but if I can just develop the two equations with algebra, that means any isosceles triangle can use these formulas, okay? What we're missing is the hypotenuse. So if I want to calculate the perimeter of this shape, the perimeter is the length all the way around, I need to know what the special hypotenuse is going to be if my two side lengths are A's, okay? So here's what we're going to do. A squared plus B squared equals C squared. That gives us the hypotenuse when we're talking about a right angle triangle. But both side lengths are the same, and I chose to call them A. So the B here becomes an A, and we end up with A squared plus A squared equals C squared. When you have an A squared plus an A squared, that becomes 2A squared. Well, how do I find the hypotenuse C? If I have it equal to 2A squared, I have to destroy the square, and what destroys a square is a square root. Now, when you square root 2 times A squared, basically what you can do is just square root the 2 separately and then square root the A squared separately. If you square root A squared, you just end up with an A. The root 2 becomes a 1.414. If you root 2 on a calculator, and I'll show that to you right here, square root of 2 is 1.414, and it's got a whole bunch of extra stuff to it, but we're going to just round it off to 3 decimal places, all right? So we end up with a hypotenuse value of 1.414a. That becomes the new special hypotenuse when we're trying to optimize a right angle triangle, all right? So what is the formula for the perimeter going to look like? Well, the perimeter is the addition of all 3 of those sides. So we have A plus 1.414a. These are all like terms. You can add them together. You have 1A plus 1A, which is 2A's, plus 1.414a, and that gives our perimeter of 3.414a. And that's the formula you need to remember for optimizing a right angle triangle's perimeter. All right? This formula will now work for all right angle isosceles triangles that we are trying to optimize. And remember that optimization means either finding the minimum perimeter or the maximum area. So how do we then find the maximum area? So to show you this, I'm actually going to show you a numerical example. Let's set our perimeter to be 25 meters. How would we then calculate the area? Well, if I set my perimeter equal to 25, I can now use this formula up here to calculate what the side length of that triangle is going to be. And the side length is going to be calculated like this. So we have 25 is equal to 3.414a. I have to divide 25 by 3.414. And that gives 7.32. So I just rounded it off to 7.3. That gives a hypotenuse length of 1.414 times 7.3, which is 10.32. So I now know everything I need to know about that triangle. What about the area? Well, we know that area is equal to base times height over 2. But if we go back to the picture here, look at my base and look at my height. The base is A, the height is A. Both of those values are the same. So instead of writing base times height over 2, we're going to use a slightly different version of that formula. We're going to use A times A over 2. My A is the 7.3 that I got over here, and that gives me my area. All right. So for a right angle isosceles triangle, your perimeter is equal to 3.414A, where A is the base and the height of the triangle. Your area becomes A squared over 2, which is base times height, A times A over 2. And with those two equations, you can now optimize a right angle triangle. Now, I here gave you the perimeter first, and we calculated the A value to calculate the area. But I could give you the area first, and you could then calculate the perimeter. So maybe we should do an example of that. So here's an example of that. So let's say you were given the area of a right angle isosceles triangle that is 32 square meters, and it says find the minimum perimeter. So the fact that this is an isosceles triangle, we already know that it's optimized, but they specifically said find the minimum perimeter, which also means we need to use those two new formulas. So we know that that perimeter is equal to 3.414A. And I just want to double check that because I'm worried that I might be getting it wrong. 3.414A. We know that the area is equal to A squared over 2. So to calculate the perimeter, I first need to start with my area calculation. So that's the first thing I'm going to do. So I'll start over here. We know that the area is 32. That's equal to A squared over 2. And now I have to isolate A. So algebraically, the way we do that is we're going to first multiply by 2. That's going to give me 64 is equal to A squared. And then I'm going to square root. So A is equal to the square root of 64, which is 8 in this case. My second step then is to calculate the perimeter. Well, the perimeter is equal to 3.414A. A is now equal to 8. And I can calculate my final answer as 3.414 times 8, which is equal to 27.3. Let's round it off to 27.3. And whatever the units are, meters, centimeters, whatever. And that's how you optimize a rectangle and a triangle. Optimizing a circle is easy. It's the regular pi r squared for the area, 2 pi r for the circumference, because there's no other choice for a circle. You can't change those equations. But for a rectangle, you're technically actually doing a square when you're optimizing. Use the equations for a square for a rectangle. For a triangle that is right angled, the optimized shape is an isosceles triangle. Use these two formulas. The P is equal to 3.414A and the area is equal to A squared over 2, and you should be good to calculate those answers. So that'll be the end of the lesson. We'll see you again soon.